Hello, everybody. Thank you all for your interest in the topic of collaborative robotics and in the Rossini project, a European project funded under the Horizon 2020 research program. This recording is the English version of a webinar provided by CRIT on March 2020. CRIT is a partner of the Rossini project and task leader of the state-of-the-art deliverable that will be presented in the following. I am Riccardo Masiero, Technology and Innovation Advisor at CRIT, and I've led the writing of the Rossini State of the Art. In detail, during this talk, we will briefly see the whole consortium of the Rossini project and discuss on the overall project scope. Then I will start by illustrating the Rossini use cases that involve three big companies of different sectors, EMA, Schindler, and Whirlpool. After the use cases, we will go through all the conducted state-of-the-art, speaking about both architecture and technologies. The Rossini's consortium entails 13 partners and 7 EU countries: Italy, Spain, Switzerland, Greece, Germany, Belgium, and Netherlands. More information about each partner can be found on the project website at www.rossini-project.com. In this slide, we report in a nutshell the scope of the Rossini project. This first sentence may be the project's payoff. As a matter of fact, Rossini wants to balance between efficiency and safety. Efficiency of the traditional robot solutions that, from one hand, are fast and efficient, but to the other are intrinsically unsafe and usually require cages for protection. And safety of the collaborative robots or cobots that are intrinsically safe, even thanks to sophisticated sensors mounted on them, but slow and less efficient than traditional solutions of advanced automation. That's it. The Rossini project aims to research and develop a modular and scalable solution, fast and efficient as a traditional robot and safe as a cobot. Let's now see together the three use cases to be realized within the Rossini project. I'd like to start with this slide to tell you about a nice idea of the Rossini's coordinator, data logic. At the beginning of the project, December 2018, according to the project plan, we had to visit the three use cases and corresponding facilities. The data logic's idea has been to do this all together in a 3-day trip. By bus, we departed from Bologna to reach Locarno and then Varese. After each visit, all the participants took part to brainstorming sessions to analyze the use cases and define the first needed requirements. Overall, it has been a very nice experience to know each other and pave the way for the next steps of the project. Going into the details of the use cases, we can start with EMA, world leader in the production of automatic machines. Among those produced by EMA, this machine to fill tea bags and pack them into a box is the object of the Rossini project. The main objective is to find a suitable cobot solution to help operators loading and handling packaging material that comes into heavy coils. EMA already engineered a cobot solution in the shop floor, but it needs to be improved in efficiency and productivity. Furthermore, EMA is looking forward a cobot solution able to automatically recover machine from micro stoppages. The challenges of this use case are the current slow speed of the AGV, namely the mobile robot that mounts the robotic arm, the impossibility to distinguish between a human and an inanimate obstacle, yet by which it will be possible to keep higher speed than those required when approaching humans, and the still limited human-robot interaction. The foreseen solution for this use case includes a new integration in terms of mobile robot and robotic arm, AI technologies to recognize humans, and a new sensing layer concept that Rossini aims to develop. and that is called RS4, acronym for Rossini Smart and Safe Sensing System. The next use case is the Schindler's one. Schindler is a world leader company for providing elevators, escalators, and moving walks. In this use case, we have a lean certified assembly line of elevator panels. This line is currently full manual and made of two steps, the kitting station and the assembly line. The overall objective of Schindler is to both improve job quality in terms of ergonomics and increase efficiency in terms of productivity. This is foreseen by redesigning the whole layout of the production line so that to move from a solution where kitting and assembly are separated to a solution where they are realized together in the same space of the shop floor with robot and human operators working together. One first challenge of this use case is the large varieties of layout combinations for the elevator panels to be manufactured. This is due to the high customization requirements for these kind of products. Another challenging element is the close interaction between the robotic arm and the operator. Commenting these, I always like to refer to the first scenes of the Iron Man movie, where Tony Stark is working in the cave to build, let's say, his first armor prototype. Here I imagine almost that kind of interaction. The foreseen solution takes a collaborative but robot arm, with suitable speed and reach, and a redefinition of the current way of working. Whirlpool is the third use case presented in Rossini. Here we have two assembly lines of washing machines. The overall task to perform is the pick, place, and fix of counterweights that might be quite heavy, up to 13 kilos. Therefore, the first objective is to improve the job quality in terms of ergonomics, maintaining the takt time of the production line and designing a concept solution that can be applied also to other product lines. The main challenges here are clearly the heavy payload that the robotic arm must be able to handle, the need to respect a predefined takt time, as well as the task assignation between human and robot. For example, we need to answer questions such as, will the robot help to the operator also in the screening activity or just for placing the counterweights? The foreseen solution is either a safe by birth arm or the possibility to use the sensing layer of the Rossini platform with industrial robots. Furthermore, also in this case, we will redefine the current way of working. Now, in order to see how the Rossini project wants to realize the illustrated use cases, let us take a look to the state-of-the-art conductive to pave the way for these realizations. As first step, this slide reports on main concept presented for Rossini. The idea is to keep in mind is the coexistence of two separate communication and on top of these control channels. The one for safety in red and the one dedicated to the implementation and optimization of the production process in blue. In this slide, instead, I want to introduce a standard representation of building blocks for a robotic system that will be useful to present in the following the various contents of the Rossini state-of-the-art. In fact, Rossini is built of work packages that can be easily mapped in these building blocks. For those of you that are not used to European projects, it will be enough to explain that such projects are usually organized in modules called work packages. A work package is therefore a set of activities that address a specific topic to be realized within the project. In the following, we will mention the technical ones, since they can leverage on the results of the presented state-of-the-art. In this slide, you can see how is organized the state-of-the-art in terms of chapters and sections. For the editing of the state-of-the-art, each of these chapter sections have been assigned to a partner as editor and to a different partner as main reviewer. The whole deliverable that is publicly available on the Rossini website, where it can be downloaded, has been then reviewed by all the consortium and finally by the European Commission's project officer that suggests us to present each section as reported in this slide. From the vision and needs for Rossini to those identified for the use cases, till the key innovation expected by the project. Since I believe this approach improves the presentation clarity, I will leverage on it in the following. Let us now start with the actual illustration of the Rossini state-of-the-art contents. The first chapter is about detection and tracking of the working environment and is related to Work Package 3 and Work Package 4. This part has been written with the major contributions of DataLogic and Iris. Considering the building blocks I've previously introduced, we are now addressing all the aspects that relate to how the robot can sense the surrounding environment, how it acquires the corresponding data and elaborates them to build the so-called semantic map. And here we are in the perception block. All these aspects are intimately linked with the Rossini sensing layer, called RS4. RS4 stands, as previously mentioned, for Rossini Smart and Safe Sensing System, and it is the link between the environment and an efficient and safe robot movement in the working space. RS4 is made of a set of sensors based on different technologies that work together. Roughly speaking, RS4 is an hardware and software solution for data fusion, with the overall objective to realize precise mapping, object localization, and 2D, 3D object reconstruction. The first need for Rossini in this context is to identify and select the enabling technologies with a focus on safety-related solutions. In particular, the investigated technologies have been analyzed considering parameters as robustness, predictability, reactivity in real time, the possibility to configure them for the worst-case scenarios, and to conjoint measure distance and speed of an object. In this slide, an overview of all the investigated technology in the deliverable. You can find a description and a discussion for each of them in the publicly available material. Concerning Rossini, the state-of-the-art output allows us to select those technologies to monitor along the project. The most suitable ones will be adopted when necessary or when a sufficient degree of maturity is reached. Similarly, a large set of references for data fusion algorithms has been selected, described, and discussed from the point of view of safety and the real-time functionalities provided. The deliverable describes both more traditional approaches and newer or hybrid ones. This large set of algorithms provides the consortium with a solid knowledge base for the future developments. As main insight from this part of the state-of-the-art, we notice that there is a lack in the current technology for continuous tracking of both speed and position. Concerning the use case needs, it clearly emerged the indication to identify well-characterize the different moving areas of each use case. In this manner, it will be possible to equip such areas with different and most suitable kind of sensor. Finally, expected innovation that Rossini will bring to the current state-of-the-art are a whole framework able to orchestrate heterogeneous technologies, connected via both safety and not safety buses, and a dynamic mechanism to adapt robot behavior according to the task to perform, the foreseen interaction with the operator, and the actual human-robot relative position. Let us move from the sensing and perception system to the safety robot architecture, Work Package 5. Here, the main contributions to the state-of-the-art have been provided by Unimore, Whirlpool, and Pilz. This topic is related, recalling the previously seen building blocks, to the solution that can be implemented to let the robot decide what to do in the environment, the so-called cognitive layer, and make it to do it, namely the implementation of the control and actuation steps. Here, the needs for Rossini are those recalled in the website. First of all, a safety step, then a mechanism to end guiding the robot, a speed and distance monitoring system that we already mentioned before, since it is enabled by the RS4 layer. And finally, a paradigm to limit power and force. With these concepts in mind, the state-of-the-art deliverable considers background technologies and real-world examples to compare them with envisioned Rossini architecture, so that to better highlight the Rossini innovative potential and spread this awareness, both inside and outside the consortium. Furthermore, a wide survey on the available technologies for both ARM and mobile robots has been done with the objective of having, from one side, a complete overview of the current market offering, and from the other, collecting the necessary information needed to do the first investments in building the final solution of one or more use cases. To sum up, this chapter of the state-of-the-art, and in particular the robot arm analysis, allows us to highlight how a low payload and a slow speed for cobots is a technology gap that must be overcome for Rossini. Considering the first need for the Rossini use cases, this is about the identification of the right arm gripper solution for each one of them. Finally, the expected innovation of the project is a mechanical redesign of a collaborative arm that will include a force feedback mechanism and will lead to an augment of the intrinsic safety of the robot. The next part is about human-robot mutual understanding and job quality evaluation, topics that frame within Work Package 6. This part leverages on the contributions of TNO and Fraunhofer IFF. In this chapter, we address two main topics: HMI, or human-machine interfaces, and environment modeling, focusing on one fundamental aspect: how to measure job quality. In particular, within Rossini, we are interested in evaluating scenarios of co-working for humans and robots, where the first objective is to define and measure job quality indices that go beyond the power and force limiting paradigm as safeguard mode. Furthermore, we would like to be able to perform preliminary evaluations about a given industrial scenario in the perspective of human-robot collaborations in terms of performance and their possible improvements. First, in this chapter, you can find a nice overview about human-machine interfaces from both a robot-to-human and a human-to-robot communication perspective. The overall objective here is to provide examples of all the different types of interaction that may lead to the evaluation of the human factor. And to evaluate the human factor, also a set of references for task allocation, job quality, and ergonomics evaluation tool is provided. From this background, a tool selection for the Rossini's objectives has been identified. This paves the way for the construction of framework of job quality evaluation specifically designed for human-robot application. In this part of the deliverable, the main observations related to the current technology gap are on the fact that there is a lack of high-performance robotic technologies, a missing safety assessment at the system level, and a low acceptance from the workforce towards robots as co-workers. Concerning the use cases, reasoning from the point of view of the workers highlights the necessity to identify different strategies to involve different kinds of subjects, since in some cases they are the employees of the production lines, in others the operators of the final customer. The overall expected innovation is related to the creation of a new framework for job quality assessment, specifically tailored for collaborative robotic scenarios. We are now approaching the last part of the state-of-the-art presentation that is related to Work Package 7. This part is mainly based on the contribution of Unimore and Iris. Work Package 7 is about safety system architecture, namely how to integrate the human factor within the overall architecture of the Rossini platform. This integration must be done at the system level, of course, including all the building blocks seen so far. To realize such integration, it is important to consider all the communication solutions that link the environment with the robot. In addition, the design and realization of a virtual design tool to properly define and study the overall Rossini concept is treated. The integration needs for Rossini can be summed up in this slide. In a unique platform, we want to frame both the safety and the production system, as well as the human factor. To this end, a section of the state-of-the-art deliverable is dedicated to the issues related to the integration of the human factor within the Rossini architecture. In particular, two key elements emerge from the conducted analysis: the necessity to build reliable human behavior predictors and to include in the platform designed, robust, and effective robot-to-human feedback solution. As overall outcome, a list of useful considerations and references for the future development of the project has been provided. Finally, concerning the virtual design tools to realize, several open and not open source programs have been identified, investigated, and compared against each other. The result of this comparative analysis is the identification of Gazebo among the open source solutions and VREP among the not open source ones as the best tools for which to start building the overall Rossini solution. To conclude, we can say that the current state-of-the-art gap as regard to the Rossini project goals are three trends: an increase of complexity and unpredictability of advanced automation solutions, a lack of robot integration along with a lack in programming expertise, and finally, a tendency to productivity loss for guaranteeing safety. All these trends come from market analysis conducted for the project proposal and included in the state-of-the-art deliverable itself. Supported by them, the corresponding use case needs have been identified and listed here, starting from improved ergonomics, easiness of programmability, simplify the production layout, simplify human-process interaction, maintaining production efficiency, and exception management. The Rossini project aims to fill the current gap and answer all these needs with a unique platform. A unique platform that defines an architecture based on heterogeneous technologies, a design tool and a risk assessment procedure to apply the Rossini concept to different scenarios, and last but not least, a job quality evaluation framework specifically tailored for human-robot collaboration scenarios. This concludes my talk that I hope you found interesting and useful. If you have any question or comment related to the state-of-the-art deliverable of the Rossini project, or more in general, to the Rossini project itself, do not hesitate to contact me or visit the project website www.rossini-project.com. Thank you.